All right, quiz was pretty good. I didn't do the average, but I think on OneNote, or I'm sorry, on Canvas, they'll show you the average for each assignment. Is that right?
It's like an 8.3, I think.
Yeah, it was pretty darn good. And that's including a few zeros where people didn't even show up and you got zeros. So that's a pretty good average for a quiz. All right, today, what I'm planning to do is go through the section on other probabilities. I started that, right? I didn't finish it. Can anybody tell me the last thing I talked about in class? Was it the Erlang distribution? Did I talk about the exponential distribution? I did. Erlang comes after that. I'm going to do this. So remember we talked about the mean time to failure of anything, and I forgot the example I did, but all right, we did the uniform distribution, and then we did the, I put up the exponential distribution, right? I'm just going to start there. I want to go through these because this stuff, some of this stuff is very, very important, and some of it's sort of just it's additional information. It's not necessary, but this one's kind of important. And a lot of this has to do with data traffic. So, in general, for the exponential distribution, this is the probability that a failure occurs. So, it's f of, I'll put exponential. And this is the density function, and this is going to be, I don't call it t, is going to be 1 over tau bar. Tau bar is the mean time to failure. And times exp, and it's minus t over tau bar. Now, this is the mean time to failure, assuming a failure occurs to the next failure. Y'all with me, class? I think we did an example of this. Tell me, y'all remember this, Eloise? How many remember this? Do you remember it or not? You said we did the exponential.
I thought we did.
I don't
Maybe.
think we did.
All right, maybe we did, which is good. So the mean time to failure is given as this. Now, let's see. So there's an example in the book, and I wish I had the whole thing written out, but I'm going to go ahead and do it. And this is in the old book I'm using. I can use the new book, but the only reason I'm not using it right now here, the book that I recommended for this class, his problems are a lot more involved than, it doesn't show the simple principles. That's the only reason I'm using this. And I'm going to go back to that book shortly, but I need to get through this stuff. So it says, as an illustration of the application of distribution, suppose the component's failure is independent, all right, an average time between failures is 100 days. This is on page 93 of this text, and I put the PDF of the text up, right? So it's saying this is an example that suppose the mean time to failure is 100 days, and it starts a 200-day mission with all components functioning. What is the probability it will complete the mission without a component failure? That would be 1 minus the likelihood or probability that it fails. Y'all with me, class? So first we're going to find out what's the probability it fails within 200 days. That's the mean right there. We're just calculating the probability of failure. Y'all with me? Or I mean within 200 days. So if the actual time is 200 days, right here, the likelihood it's going to fail, and just for everybody's sake, if we take a look at time and look at this distribution, the 1 over the mean value times exp minus t over tau bar, which is that, it looks like this. And this value right here is 1 over tau bar. Now, if you integrate that, you'll get a value of 1. So this means the probability of a failure, and I'll say P of failure for T less than, I'll say 200 days right here. That's the integral from 0 to 200 of 1 over, and this is 100 e to the minus T over 100 dt, and I'm just putting in the values into this function integrate. If you get this, you find out it's going to be equal to 1 minus e to the minus t over 100, or it's really 1 minus e to the minus, and it's going to be 2 right here, because t is 200, the mean time is 100. Do y'all follow me on this? And I don't mean to go too fast. Y'all with me? That's the probability it fails at 200 days. By the way, in general, I mean that when you integrate this function, if this is my f of t right here, if you take a look at a probability of a failure, this is going to be a failure within t anytime from, and if we integrate this from 0 to t of 1 over the mean time to failure of exp to the minus, and I've got to use a different variable, so I use minus x over t dx. This is the probability of a failure between 0 and t. If you integrate this, what you get is going to be 1 minus exp of minus t over tau bar. That's a probability for an exponential distribution that fails between 0 and t. Y'all with me? So the probability it doesn't fail is 1 minus that. All right, this is the probability of a failure. For t less than 200. And that means the probability it doesn't fail, probability of no failure, t less than or equal to 200, is just 1 minus this, or 1 minus 1 minus e to the minus t over 100, or actually 200 over 100, or it is just e to the minus 2. Y'all with me on this? This is not hard to see. Now, one thing you're going to see, that the probability that it doesn't fail as time goes to infinity, goes to 0. Do y'all see this? Just take a look at this argument right here. This is the probability it fails. So the probability it fails as t goes to infinity is going to be 1. That means the probability it doesn't fail is 0. Y'all with me, class? How many see this right here without me going too fast? All with me on this? All right. Now that's the exponential distribution. In the book he asked for a few other things, and this is on page 93. Then he gives an example of a traveling wave tube. I'm going to ask somebody. Y'all with me on this, class? Can you do me a favor and just read the second example? I want to go through this because the Erlang's the next distribution, and it really is, suppose you got an exponential distribution for time to failure, mean time to failure. Well, what is therefore the actual value of the mean time if you have for 4 failures? We'll get to this in a second, all right? Not just, oh, you got it right there? Okay. So go ahead. This is second example, and I'll slow down.
Consider a traveling wave tube.
Do you know what a traveling wave tube is? You know what a vacuum tube is? How many do? All right, traveling wave tubes have to do with microwave energy. I'm not going to get too far into that. You know what magnetrons are? Anybody? What's a magnetron?
Thing in a microwave?
Yeah, when was it valuable? World War II. It allowed radar to work because it was a high power source for microwave energy that was stable. All right, traveling wave tubes, all these things are related to high frequency microwave energy, and they have to do with creating it and amplifying it. Go ahead.
Used as an amplifier in the satellite communication system, and assume that it has a mean time to failure of 4 years.
4 years, okay, go ahead.
That is the average lifetime of such traveling wave tube experience, although any particular device may fail sooner or less than a decade.
All right, so this is 1 over tau. This is actually the density function for failure is going to be 1 over tau times exp to the minus t over tau. I'm putting the density function because I wanted you to get a mental picture. Anytime you're talking about a probability of failure between point A and B, you just integrate that thing, you got the probability of failure. Got that, class? Now that, to me, is simple. What does he ask?
He says, for example, the probability that the traveling wave tube will survive for more than 4 years is.
Okay, how do we do that? What it's really saying is the probability, if we come out here 4 years, right? and we say the probability of failure, it's this area. Are you with me, class? So 1 minus that would be the probability of no failure, right? And he asked for the probability of no failure. Do you agree with that?
That is, yeah.
Y'all with me? Now, it's always going to come down to this. The probability of no failure, I'm just going to put no fail for time t, is 1 minus the probability it fails. Well, the probability it fails is 1 minus, they're really going to be just, because it's integrated, exp to the minus t over t. This will always be the case, or it's just exp, this is the one thing, the takeaway from this, minus t over tau. That's the probability of no failure up to a point t. The only thing it is the exponent. exp to the minus t over the mean. Now, if you think about that, that's the probability of no failure. What happens as t goes to infinity? It goes to 0. There's no chance it doesn't fail. That's the only thing. So for this one, what is it going to be for this? It's what? It's just exp, right? To the minus, well, t, they said 4 years. It's 4. The mean time to failure is 4, so it's e to the minus 1. What is that? About 0.3, what? 368? Is that what he has in the book? I think he does.
0.368, correct.
Y'all with me? Okay, what's the next part to that? Just follow me. Make sure you see it's simple, really. Go ahead.
The probability of it failing in the first year.
All right. Now, what is that? That's just this area under this curve right here, right? Trying to make sure you see how simple this is. It's that area, right? With me, class? What's that area going to be? Well, if we integrate this function, dt, from 0 to the point 1 year, that would be the probability. Do you agree? When you integrate this, you'll notice with respect to t, you get 1 over tau. This goes away, and you get 1 minus, really, the probability of failure, period, for a time t is going to be 1 minus exp to the minus t over the mean time to failure. And that's simply going to be 1 minus exp, and now it's going to be minus 1 over 4, because the mean time to failure was 4 years, right? What is that value? Can somebody do that?
0.221 is what he has in the book.
0.221? Okay. Go ahead. This, by the way, this exponential distribution is used a great deal when you talk about the probability of, when you deal with communication systems, that a system will be open to receive or open not to receive information. But we'll talk more about that later. Go ahead.
Probability that it will fail between years 4 and 6.
All right, somebody tell me how to do that. What are we really talking about? We're talking about the area between what? 4 here and 6, right? It's this area would be, under that curve, would be the probability it fails. Do y'all agree with that? Can everybody see this? All right, I'll slow down, I'll try. I'm going to do it over here. So what is that probability going to be? If you think about this, the probability it fails at any point in time is this, right? So if you want the probability between 4 and 6, well, 4 would be what? Greater than 6. Do you agree with this? The probability it fails within 4 years is less than the probability it fails within 6, right? So you take the probability, y'all with me on this? So what does that boil down to? The probability of it fails, and this is a failure for t greater than 4, less than 6 is really what? E to the minus 4 over 4, right? If we do we could write it all up. Y'all with me on this? Minus what? E to the minus 6 over 4, right? And that's e to the minus 1 minus e to the minus 1.5, and I don't know what that is, but that's it. It can't be negative. Remember, the probability of something cannot be negative. If you get a negative, switch them. You got them wrong. What is it?
0.1447.
All right. Is that the answer in the book?
That is the answer in the book.
Y'all with me? It's straightforward. Got me on that? All right, is there another part to that one?
The last question is, find the probability that the traveling wave tube will last as long as 10 years.
Okay, how do we do that? I'm gonna erase this. I think you see it by now. What's the probability that it'll last at least 10 years? Anyway. Well, the probability it fails within 10 years is just the integral from here to 10, right? So 1 minus that would be the probability it lasts 10 years. Do you agree with that? Anybody know what that is just by looking at it? The probability that no failure for t, I guess, equal to 10 years will be what? It's going to be 1 minus quantity 1 minus exp to the minus 10 over 4, right? Or really it's just exp to the minus 10 over 4, or it's exp to the minus 2.5. Do you agree with this, class? And what's going to happen for the probability of no failure when it goes to 20 years? It's going to go to 0 eventually, right, as we increase time? Everybody with me on this? How many see this right here? Now, I'm not trying to make light of this and just speed through it, but this actually is pretty intuitive. You think in terms of the area, if this is the likelihood or the probability density of failure, anytime you're thinking about the probability of success, it's 1 minus the probability of failure. So figure out the probability of failure, subtract from 1, you got the probability it doesn't fail. Okay? All right. Is there another part to that one?
Yes, sir.
All right. I think the next one, but I'm not sure, is Erlang distributions. Yeah. Now, Erlang's kind of interesting, and I'm just going to tell you in the book, it says, I'm going to just read it right from the book. It says the random variable in the exponential distribution is the time interval between adjacent events, or first failure, second failure. Got me? Or if you start at 0, from 0, the time the switch is flipped to the time it fails. That's what this is. Now, it says this can be generalized to make a random variable the time interval between any event and the kth event. So if you think about this, what is the probability density function for not 1 failure, but for 4 failures, or 3 failures, or any number of, quote, failures, or any, they say failure, but any outcomes that the density function reflects the probability of. With me? So, has anybody used Erlang? It's very similar to Gamma. This is stuff you get later when you're seniors and stuff. You'll, depending on how many are going to take any kind of courses in communications or wireless communications or anything like that. You're going to be taking things that are related to this very distribution. That's the reason I just wanted you to pay attention to this one. In radar, I don't use, at least I haven't used this one that much, but I'm aware of it, and I forget where else Erlang's used a lot. But it's primarily, it has to do with, if you take a look in that section on Erlang, doesn't he say it has to do with data traffic for telecommunication systems or something like that?
Is that still in the same?
It's right at the bottom of the exponential, it's Erlang. Right after the last example. You keep reading on, you'll see it. I'm gonna put it up there.
You call it
The what? It's called Erlang, E-R-L-A-N-G.
It says it's like telephone systems and traffic systems.
It's data, yeah, data communication. It has to do with available lines. If the mean time of an available line, single line is exponential, then the accumulation of, you know, you're going to have all sorts of data traffic. And I'll try to be clear about this. Sometimes I struggle for the exact correct words, so just bear with me. But you got to think about this. What's the one thing when you do data traffic, when you think about the internet? Well, it's the availability of the actual port that you're going to being available, basically. You know what what do they call that, a flood ping is and stuff? Have you all heard this? Basically, if you just keep sending information back and forth to a server at such a rate that the time it takes to actually respond to that from the next pulse coming in is great, so the server can't look for any other people that are seeking that line. You'll follow me? Because there's so many available lines. And if one line just has nothing but data traffic coming into it, can never get off there to see if there's anybody else that is looking to get into that system. Are you familiar with this principle? What do they call it? Flood ping, right? Has anybody heard this? Flood ping or anything like that?
Yeah.
You have. Good. This is what this distribution is about. So when you talk about the Erlang distribution, and I'll be the first one to say, I don't use this a lot. This has to do with the exponential distribution. The exponential distribution has to do with the probability of a failure after a failure or the beginning of the event to the time of failure. Now, here we're going to say not just one failure, but we're going to have 2, 3, 4, 5 failures or 5 events occur. And I don't like the word failure because when a data line becomes open, I don't consider it a failure. But that's how this thing's crafted, the verbiage here. So for an Erlang distribution, and I'm going to use, he uses tau, I'm going to use, yeah, I'll use tau. So he says for an Erlang, right here, this is the density function. I'm going to use tau, not t. It's going to be this density function to the k minus 1. K is going to be the number of events occurring or failures for us. I guess he's into the failure mode. Then it's going to be over, remember, K is the number of failures. Follow me on this? Before, it's the time of failure to the time to just the first failure. All right. Now this is going to be the time to the nth failure. This is the statistics. Then you're going to have over the mean time to the kth power. So that would be the mean time to failure of the first one. There's a proof for this, by the way. I'm not going to do the proof, but I may put it up on OneNote. But then it's going to be times the way he has it. He's going to have over k minus 1 factorial. You tell me if I'm wrong here. I think that's what he has in here. And then he's going to have times exp to the minus, and it's going to be tau, which is the time over t bar. And I think he has it that way in his distribution. Yeah, and this is equation 2.44. This is equation 2.44. And by the way, this is only for tau greater than or equal to 0. It's equal to 0 for less than that, but that's sort of obvious because anytime you talk about a mean time to failure, if it started t equals 0, you can't go back in time. It only has to do to the failure of the next event. Okay? Now, a lot of these distributions do apply to things that are not monotonically increasing functions of time or space. They can be distributions that have to do with plus and minus, like with the Gaussian distribution, right? You could have a positive or negative value for the random variable. Here, it can only be positive. Okay, so for that Erlang distribution, it's also related to the beta distribution on page 95, but I'm going to tell you, I'm going to use this in some problems. I want to expose you to this, and the reason I'm saying this, you see how this is really time right there? So it's time, and it's not going to be the first power, second power, third power. It's going to be the nth power. So when you do the integrations, if you wanted the probability it fails using an Erlang, if you want probability, and you should write this down, of a failure between 0 and greater than, or k failures, probability, it should be of k failures, k fails, from 0 to some time t, that's going to be the integral from 0 to t of that distribution, which is going to be tau to the k minus 1 over the mean time times k times k minus 1 factorial times exp to the minus tau over the mean time to failure. It's in your book, d tau. Now you look at that, that integration is not something that has a closed form solution. This is t right there, so it's going to be like t squared, t cubed, t to the 4th times the exponential. So those integrations aren't easily done analytically because you're going to do integration by parts a lot if you do these. But there are There's tables for this in your calculators, thank God, do this. I think you have Erlang on your Inspire, I think. You check it out.
It's not labeled his name, but there might be.
There's got to be a gamma function. Gamma is the same thing as Erlang, it's the change of variables, and that's equation 2.2-445 on page 95. You just make a variable change. Isn't gamma function in yours? G-A-M-M-A? I'm almost positive it is. Yay or nay?
You see geometric Poisson.
Okay.
It could just be called something.
You got gamma in yours? I'm sure the HP does. Yours does, doesn't it?
I'm searching the manual for
Either gamma or Erlang. Probably
it.
gamma.
I see it has gamma on it.
That's same thing as Erlang. All right. Now, to be fair with you, I'm not going to ask you a problem specifically on this. It gets complicated. If anything, I'll tell you the kind I would do. It would be like 2 events, and we'll do that one. Okay. Next, I did delta distributions, didn't I? Or not?
Yeah. Oh, wait, no.
No.
Okay.
Sorry.
We're gonna do. Now, what's a delta distribution? If you have discrete events only possible, coin tosses. You got either a heads or a tail, right? 3 possible outcomes, 4 possible outcomes, stuff like that. That's a delta distribution, okay? So, in the book, can you tell me the first problem in the delta distribution? He has just 2 events, right? He says if we have something that has 2 possible outcomes, say x1 is an outcome. If we talk about x itself, its outcome possibilities are x1 and x2. There's only 2 outcomes, heads, tails. Think of that, all right? The first one, x1, has a probability of p, and that means x2 has a probability of outcome of 1 minus p or q. Now he'll label this as P1 and P2, but you can see if you only have 2 possible outcomes, the first outcome tells you the probability of the second. Not percentage-wise, but in terms of fractions. You all with me, class? Fractions of 1. So what does the distribution of this look like? The actual probability density function. The book that I recommend, or that was given for me to the class in the beginning, given for the class, in that book, they call it a probability mass function. It just means it's only for discrete values. It's the same thing as a probability density, but it only has delta functions. So the probability mass function for this would look like, if this is x, here's x1, here's x2, and it's just a delta function. This is going to be p1 in height, right here, and this is going to be p2 in height. Everybody follow me? Think of heads, tails. They're both 0.5, right? All right, now what's the mean value of this? And think of the definition of mean. If we have a continuous random variable, when we talk about the mean value of anything, we think of integration of x times f of x dx, right?
Yeah.
If you have a discrete random variable, the integral becomes a sum, then it becomes over I equals whatever, from 0 to n minus 1 if there are n possibilities. And then it's going to be the value x of I times the density function f of x of I. And you're going to simply sum them up, and that would be the mean. It should make sense to you. And this is really, the bad thing about this, this is the probability. It's not a density where you have to integrate. It's just the probability. So maybe probability mass is a better term for that. So just think about this. What is the mean value going to be for this? For 2, it's just going to be what? Well, the first event, right, is x1, the probability is p1, so it's going to be x1, p1, and the second one would be x2, p2. And if you want to, you can make p2 1 minus p1 if there's only 2 possibilities. Do y'all agree with that? All right, that's the mean value. What's the mean squared value? Take a look. So this has got to square it. Now, what's that going to be? Start with the first value, x1, you got to square it, right? Times the probability occurs is p1, so it's x1, and it's just squared times p1, plus x2 squared times p2. That's the squared value, right? I'm only doing 2. You can extend this logically to n possibilities. Y'all with me? All right, what's the variance? Now, variance is very important because it doesn't matter the distribution. What happens? The variance of this x is symbolized as sigma x squared, so it's the standard deviation squared as well. That's the mean squared value minus the mean value squared. Do you agree with me? What's that going to be? Let's see. Mean value on this one is right there. So I got to square it. I'm just going to write it down. x1 p1 plus x2 p2 squared minus the squared value, which is x1 squared p1 plus x2 squared p2. Now you can fuss with this and go ahead and square this thing out. You get x1 squared, or x1 squared p1 squared, and then you have x2 squared p2 squared, and then you have 2 times x1 p1 x2 p2. Y'all follow me on that? And you subtract all this. In his book, he gives a compact form for that. Personally, I just do the math in the other ones and do it out. And he has it's p1 p2 times x1 minus x2 squared. So this becomes p1 times p2 times x1 minus x2 squared. Do you all see that in the book, by the way? And the only thing he's doing is fussing with this thing and just rearranging it to a nice compact form. This will get you there every time. It's easy to do. Okay, that was the delta distribution. So he gives an example, I think with coins, right?
Yes, sir.
Let's do that one here. We're going to do the problems. And class, I know I could assign the problems, put them up, and just sort of do one of those, but I firmly believe, especially for this class, working problems tells the tale better than just throwing a lot of theory out. That's my own opinion.
Do you want the in-text problems or the ones at the end of the section?
No. I want right after this. There's a problem in the chapter that has to do with coins, and I forgot what it is exactly, but we'll do it. Last night I was doing this, and I'm trying to. Everything I'm doing, I'm trying to relate to what I do with radar or EMC or stuff that I've actually deal with on a daily kind of basis, or at least more frequently, once a year. And this distribution I actually deal with. I mean, that kind of thing within possible outcomes that are discrete. All right. It has to do with the number of targets are identified in like a radar search field, and then there's a probability of these targets actually being threats or non-threats, and it's a long story. Go ahead.
When 3 coins are tossed, the random variable is taken to be the number of heads that result.
All right, so here X will say is number of heads. Go ahead.
Part 1 is the mean value of this random variable. Find the mean value of this random
All
variable.
right, before we do that, think about the discrete probability mass function or probability density function we're going to have to build for this. All right, we have 3 coins. It can be either a heads or a tails. That means the number of outcomes is 2, right? Because there are only 2 possible outcomes to the nth. There are 3 coins. If there were 3 possible outcomes for each one of these separate tosses, then we'd have 3 to the nth, where nth would be 3 coins. You all with me, class? So this is really going to have, for the number of outcomes, it's going to be 2 to the third, or 8 outcomes. 8 possible outcomes, right? So now he cares about the number of heads. I don't know if he says this in the book. This is going to be number of heads. But if you think about this, we're limited between 0 and 3. Do you all agree that he's assuming the coin's even, the likelihood of a head is the same as the likelihood of a tail? Okay, so if we talk about the number of heads being 0, what is that? The probability. I mean, sorry, think about that. I don't know how he does it in the book, but I'll just say this. If you think about that, isn't that really the binomial distribution? If we're talking about, we've got n events, we want, or k successes, right? And I think Actually, I'm not sure how
He doesn't really show anything, he just gives the answers.
he what?
He doesn't show any of the work.
Okay, well, we're gonna do it. So if you think about this, the probability of what? Okay, so when we think about this, the probability of Kn is equal to really n factorial over k minus n factorial times k factorial times the probability of success of k times 1 minus the probability of success n minus k. That's the general binomial, right? Adapting it to R's, we have P, and it's going to be K, comma, and this is going to be 3, is going to be equal to 3 factorial over K minus 3 factorial, K factorial. And then this is nice because 1 minus P is the same as P, correct, class? Right, it's 50%, so 1/2 is there, 1 minus 1/2 is 1/2. I can just make this P to, or 1/2 right here to the 3rd power, right? So just rewriting that, that's gonna be equal to 3 factorial times, or divided by 8, that's 1/2 cubed, and then I'm gonna have over K minus 3 factorial over K factorial. And here we start out with 0. The value of that is going to be simply 1/8, isn't it, class? Put a 0 in for here, right? These cancel, right? 1 factorial, or 0 factorial is 1, so it's 1/2 cubed, it's 1/8. Do you agree with that? Won't that be the same for the number of heads being 3 heads? It would be 1/8, right? Now, if you talk about for 1 head, what is it? Just take a look at this. You got 3 factorial, right? Over 2 factorial, 1 factorial, and then it's still 1 over 8 here. So this is going to be 3/8, isn't it, class? 3/8. So for 1, it's 3/8. What is it for 2? Just do it. So if we have P of 2 comma 3, what do you get? That's 3 factorial, right? That's going to be, sorry, I should put 3 minus K factorial n minus K. All right, that's going to be what? 1 factorial? And this is going to be 2 factorial, right? Times 1/8, it's the same, isn't it, class? You all agree with that? That's going to be, too hot, it's going to be, this is 3/8, this is going to be 3/8 here, correct? And then that's 1/8. So that's the probability mass function of this. Does everybody follow me on this? I'm just showing you how you would construct this problem on a quiz, test, or in the real world. All right, start with the mean. What's the mean of this? All right, we got 0 times 1/8, right? That's 0. Then we got 3/8 times what? 1 is 3/8. Then we got 3/8 times 2 is 6/8, right? Then we got what? 1/8 times 3 is 3/8, right? So that's what? That's 12/8, right? Or it's 5 by 2, you're going to get 1.5. That should be an answer in the book.
That's correct.
Y'all with me? Now, the next thing he wants is what?
The variance of this random variable.
All right, to get the variance, remember we got a form for that for 2 of them, but now for the variance, we're actually going to get the second moment. We're going to get the mean squared value, then we'll take the mean squared value and subtract the actual mean value squared and get the variance. How many understand what I'm talking about here? Are you with me? Well, let's do it. So what's the mean squared value going to be? Now this is nothing more than the expected value of x squared. Anybody? Start with 0. 0 squared is 0 times 1/8 is 0, right? Go with the next one. Now I take 1 squared is 1, times 3/8 is just 3/8, right? Plus, now I take 2 squared is 4. Y'all follow me? I'm right here. Right? 2 squared is 4, times 3/8 is 12/8, right? I'm gonna leave in terms of eighths. Plus, now I come over here, right, where am I? Right here, right? So 3 squared is 9, right? So I get plus 9/8. And that's gonna be what? So here, 9 and 3 is 12, 12 and 12 is 24, right? Eighth or 3. Do you agree with me? Just take a moment. Make sure there's nothing obscure about what I'm saying. Everybody with me on this? I'm not trying to bore you with simple problems, but it's essential here that you see why I'm doing what I'm doing. Chase, you good with that? All right, now, how do I get the variance? I get the mean squared. I want the variance. That's what?
Mean squared minus the mean.
Minus the mean value squared, right? It's a very angry term. What is it?
0.
So this is 3, this is the mean squared value, so it's 3 minus x bar is 1.5, right? Isn't 1.5 squared, right? 2.25, what does that come out to? 0.75? And I think that's in the book. Did he ask another part to that?
No, sir, that was it.
You all with me? Just out of curiosity, what's the probability of 2 or more heads? Just looking at that distribution function. 2 or more. 3/8 and 1/8. That's 4/8 is 1/2, right? What's the probability of 2 or less than 2? Huh? That's why. Or 2 or less than 2. So it's 1/8 plus 3/8 plus 3/8, right? It's all these. I'm just showing you how to think about this. And I gotta say, some of this stuff is so simplistic. When you see it, it's like, why are we even talking about it? It's too easy. But sometimes you don't see it, and then it's confusing. Everybody with me on this part? The next distribution, I don't know if I covered them all. All right, we talked about the delta with coin tosses. He gives a signal there, but I'm gonna tell you what I'm gonna do. I'm gonna get right to the problems because I got enough time to do them. So if we go into chapter 2.7, can you get there and we'll do them all? Because here's where the solutions are up there, but I want to go through them. Some of the answers I think are wrong. I know they're wrong. But at least his method or his ideas are correct when he constructs the solution. We're going to get into conditional probability and also we're going to get into the Rayleigh distributions shortly. And you'll see how all this stuff will make a lot more sense when you see them applied. Then we'll jump into the other book and move into a lot of things with conditional probability and related to a lot of events that are common. So for that problem, 2.2-7.1, go ahead.
Oh, dang it.
Pardon me?
I saw a number.
I think it's x is equal to cosine of theta, as I recall. And the density function for theta looks like this. So theta has values from 0 to 2 pi. And that means the density function has a peak value right here of simply 1 over 2 pi. That's what you get. Y'all with me, class? Now, if you think about a cosine, if x is cosine theta, just think about this logically. A cosine function does this over a period. This is 2 pi right here, and this would be the x of theta, this cosine of theta, right? Just, I want you to get a visual on this one, and I'm going to slow down. Everybody with me? Now, the first thing he says, this is the density function f of theta, and what he looks for is the density function f of x, right? That's the random variable x there. Y'all follow me? Now, if you think about this, and I thought about the best way of explaining it, I'm gonna try to do it with visualization. It always seems to help me the best if I can visualize what I'm talking about. So if you think about this, if you take the probability, if you want the probability of x, if this is dx, or dx here, then when you take a look at d phi here, and there's also going to be a d phi here. Y'all with me on this, class? I'm just trying to give you a visual. If you think about, like, we knew the probability that would be a certain value, a d phi times the probability of f of phi. That would account for the probability of this having these values on this side, but then we'd have to add this on this side. You all with me, class? Follow me? Now, just think about this. That's a constant value. Therefore, when I talk about this, it's equally likely that any values would occur for theta, right? Out of curiosity, if that's the case, what do you think the average value of that would be? First, I'm going to come back to the density function. Well, what would the average value be, which is the expected value of x? That would be the integral, there's x, right, of cosine of theta times the density function, which is 1 over 2 pi d theta from 0 to 2 pi. How do you know what that is just by looking?
Divide by square root 2.
Take a look. What's the integral of any trig function over one period? I mean, of cosine or sine over one period? It's 0, isn't it? So the probability, or the mean value of this is 0, right? You follow me on this? You're getting an idea. Now, if you think about this, what I'm really looking for, if I want f of theta, d theta, equated to f of x dx. This is the probability, it's probability density function times d theta would be equated to the probability density function now of x dx. And I hope this is making sense to you. You all with me? All right, that means if I rearrange this, and I got to talk my way through this, if I look at f of x, now I'm taking this to the other side, that's going to be equal to f of theta, and then it's going to be times dx d theta. Now, bear with me. You with me on this, class? The only thing I'm doing is, if I got this, and that's where they always start, the thing I have to note is there are two possibilities. For every, you might say for any value of x here, there are two possibilities of theta here. That's what I'm trying to get at, or d theta here, two ranges. So if I take a look at this, I know that f theta right here is a constant. It's 1 over 2 pi. Now I've got to take a look at dx d theta, and this is in his book, by the way. So if this is x is cosine theta, dx d theta right there, derivative of cosine is minus the sine of theta, right? You agree with me, class? If you take a look at that, then I can go and say, down here, this is going to be 1 over minus the sine of theta. And then I take a look at this proof, the sine squared of theta plus cosine squared of theta equals 1, or 1 minus sine squared of theta is equal to cosine squared theta, or, actually let me do it the other way. I'm going to say 1 minus cosine squared of theta is equal to sine squared, or sine theta is equal to the square root of 1 minus cosine squared of theta. I'm just showing you what I'm doing. Now here's what he does in the book. There are a couple of ways to do this. His way's fine. Cosine is x. So that means this becomes the square root of 1 minus x squared. Would be, and it's actually got to be plus or minus that sine theta. Are you with me, class? So you can put a minus here. It's really minus plus this is equal to, plus minus that. Over here, I can replace that, as 1 over 2 pi here, and then it's going to be equal to 1, or really square root of 1 minus x squared right here. Now, because of this occurring, there are, for the positive value of x here, there are two values of theta that are possible there, or there's the density function for f of theta is twice what we need, and actually that means this goes down to 1 over pi. Now, if you write this down formally, what you have to do is take this, let me put it this way. You see how this thing can only have positive values of x? Do you all see that? It'll only have positive values of this thing. Well, if you look here, x can have negative values as well, but x squared can't. Without saying too much more, this will be the density function, and we'll get into a little bit more about how you get this. He doesn't go into it, but this is conditional probability, and this is in section 2.8 of the book I'm referencing now, and in the other book is another section on that, but I just wanted to mention this. Does this make sense to you? How would you figure out, how would you make sure that's the right density function? Anybody? Well, what do we know the expected value of x is? It's 0. Remember, that's the expected value of the cosine, isn't it, class? So what we could do is take this density function right here. We could do what? Integrate it from x equals minus 1 to 1. Take that density function, 1 over the square root of x squared minus, or 1 minus x squared, dx, and integrate that, right? You all agree with that? Now, hear me. You don't have to do you know the answer, it's 0. What kind of a function is this, even or odd? Even function, right? Even, when you do the integral, since this is the probability density function, we're going to get, what, this is the mean, or sorry, this is the probability is 1 here, right? I'm sorry, I should, y'all follow me? If you take the probability density function, integrate over the range, it has to be 1. It is. I'm not going to do it, but it is. But now we're going to get the mean value of this. So if I want the mean value of x, what does it come down to? It will be 1 for that one, I know that. I didn't put the probability in there. But the expected value of x using, the expected value of x using the density function from minus 1 to 1 of x divided by the density function, which is going to have a pi up top that I omitted last time, over the square root of 1 minus x squared dx. This is the one I should have talked about. Y'all follow me? I take the density, or take x, and I multiply it by this. This is f of x, pi divided by the square root of 1 minus x squared. Is everybody following me on this part? I want to be clear about this part. Now, this right here, the 1 over the square root of 1 minus x squared, square root of that, that's an even function, but x is an odd, right? So the integral of an odd times an even over a domain from minus a to a is always 0, and that proves this. Just think about it for a moment. Some of this stuff I know is a little hairy to think about, but we had a density function here that had to do with phi, right? So we've got a function of phi. The expected value of that function is the density function times the probability density function times the function times this cosine integrated over the possible values of theta. That's one way to do this. We also have it related to x, right? So if we have this x, and times the f of x, we have this times this. This is f of x right here. If we take this and integrate it from minus 1 to 1, we'll get 1, but if we multiply it by x, which is the expected value of x, right? This is the density function for x, If we multiply it by x right here and integrate, we get 0. Either way. Y'all follow me? That's the only point he's really showing you about some of this is how to construct a density function based on taking a derivative and noting that there are two possible values for this. I mean, this will have two possible values you have to account for. You got to divide multiply the 2 pi by 2, 1 over 2 pi by 2, and you get pi, simply 1 over pi there. Did I put pi on the top? I did. I'm sorry. Down here. Yeah. What's the third part of that question?
Find the variance of x.
How do you get the variance? Well, the average value is 0, correct? That means what? The variance is technically equal to the mean squared value minus the mean squared. Do you all agree with that, everyone? Since the mean is 0, everybody follow me. If the mean is 0, the variance is the second moment, right? So what's the second moment going to be? I'll put it here.
Wouldn't you just do that same thing with x squared?
That's exactly it. This one's an integration. If you look at this, we have, if we want the second expected value of this, you have to integrate from minus 1 to 1 of x squared, right? And by the way, we could do it with cosine, couldn't we? Since x is equal to cosine of theta, right? We could get x squared as cosine squared, then we could do it with respect to the f of theta, which is easier. But I'm gonna do it both ways. You with me, class? All right,
Yeah.
ready? If we do it with respect to x, what do we get? Well, we have x squared times f of x, right? F of x is 1 over pi, 1 over the square root of x squared minus, or 1 minus x squared, pardon me. 1 minus x squared, right? Dx. Now, we can do that part. Since we can make a you don't want to do that part? Well, you can do it, right? Because we can put it in terms of sines and cosines as before. Or, what's another way of getting the expected value of x squared? That's the expected value of what? Cosine squared of theta. Correct, class? Now, what's that going to be? Well, now I can say that's the integral from 0 to 2 pi. It can be 0, it can be over any 2 pi. It can go from minus pi to pi, but 0 to 2 pi in the books, we'll leave it that. And this is going to be the cosine squared of theta. And then we have times the probability density function, which is 1 over 2 pi d theta. Both of these will give us the same answer. Do you all follow me? This is using the density function of f of theta times the value, the expected value. And this is using x. Either one will give you the same answer. So what do? Take 1 over 2 pi out in front, right? What's cosine squared equal to? Isn't that?
1/2.
Yeah, you can do it that way. 1/2 times what? 1 minus 2 cosine?
Cosine 2 theta.
Is it 1 minus cosine 2 theta?
Oh, it's plus for cosine.
Yeah, cosine 2 theta, right? And we take that,
And then it's,
and then what do you have to do?
it'll be 1/2.
Integrate from 0 to 2 pi. Y'all follow me? And d theta, right? Now, if you integrate this function right here, cosine 2 theta, over 2 periods, which would be 2 periods, it's 0. Do y'all follow me? This goes away. What happens next? Well, I have 1 over 2 pi, and then it's going to be times 1/2, right? And then I have to evaluate, when I integrate d theta, I get theta evaluated from 0 to 2 pi is 2 pi, and that's 1/2. Do you all agree with that? You can do this too, and you'll get the same, yeah, that's right, 1/2. Agreed, class? You can do that integration numerically, and I think you make the substitution.
I think you do a trig substitution so you get the same thing.
You're going to get the same thing exactly. I didn't do that last night, but for the top one, but I know you do. I've done it before. You all with me, class, on this one? I'm trying to finish this last. Let's get to the next problem, and that's problem 2-72, right? I'll move through this, but I'll try to make sure you see. Can you read that for me?
A continuous valued random voltage ranging from minus 20 volts and positive 20 volts is to be quantized so that it can be represented by a binary sequence. Are you asking for part A or repeat?
Okay, go ahead.
If the RMS quantizing error is to be less than 1%,
I want you to understand something. First, the error, quantization error. Please hear this. The quantization error is equal to delta squared over 12. That is quantization error. Now, he says the mean squared, or how does he put a square? The RMS, doesn't he say root mean squared?
RMS, yeah.
All right, RMS is the square root of this. So he says if you take the square root of delta squared over 12, this value is 0.02 volts.
Is to be less than 1%.
Oh, okay. So it's 1% of the maximum, right?
Of the maximum value of the voltage.
All right, hear me on this. The range is 40 volts, but the maximum value is 20, correct, class? So what he's saying is we want this to be less than or equal to 20 times 0.01, 1% of that, or 0.2. With me? Please just follow me. I'm trying to get through this. I need to get through this today if I can. All right, now look at this. If you take this, that means the delta is what? The delta, or the difference, the delta V, you can quantize. So it'd be 0, then this would be the delta, would be the next possible level, up or down. So this is going to be equal to a square root of 12 times 0.2, and I think that's 0.37 something. Or can you give that to me, class? Square root of 12 times 0.2.
0.69.
Is that right?
Yeah.
0.69. Now this range, the actual spread is what? I call it dynamic range of this is equal to 40 volts, correct? That means the quantization, or the level, the delta V, the difference in the levels possible would be 40 divided by 0.69, and that's like 57, I think, or 58. Can you tell me what that is? Huh? 57 point something, what? 0.7, is that right?
Yes.
Okay. That's the number of levels. Usually, when you're dealing with digital quantization, the levels have to be 2 to the n, right? Now, if you wanted to figure out what this is, if you didn't know what the next value of 2 to the n was, if you take this and you simply say, well, this right here has to be 2 to the n has to be 57.7. It's not going to be it, but I'm going to show you how to do this. You all agree with this, class? You would take the log of both sides, so you get the log of 2 times n is equal to the log of 57.7. This isn't in the book. I'm just showing you a way to calculate the value of n. It's got to be greater than this. But you with me, class? Take a look at this, and now we get natural log of 57.7 divided by the natural log of 2. You could use log base 10, it doesn't matter. That's n. What is n? It's 5.7. 5.85. Now you can't have 5.85 bits. It has to be an integer value. The next possible integer value after 5.85 is 6, right? So that means there are going to be 6 levels. N equals 6. What's the next part, please?
I think you solve
I didn't solve the whole thing, did I? It's 2 to the n is the number of levels, right?
He said the last one was asking for the binary digits required.
So that's 6. That's the last? Shouldn't it be the delta V? The delta V now with this is what? How would you get it? How many levels do we have? 64, right? Right? So you take 64 levels, right? If you divide that into 40, that would be the delta V, wouldn't it, class? Before we had what, 57.87, 57.7. But that would be the new delta V, all right? Y'all with me?